All right, so in this video, we are going to prove that a polynomial is a unit if and only if its constant term is a unit, and furthermore, if all of the remaining terms of the polynomial are nilpotent. So we're going to prove the reverse implication of this first because it's significantly easier. So we're going to assume that f is a polynomial whose constant term is a unit and such that the remaining terms of f are nilpotent. So what we want to observe is that because all of a1 through an are nilpotent, the monomials associated to them are also nilpotent elements of R of x. Right, so what that means is for any I between 1 and n, we know that there exists an mi so that ai to the power of mi is equal to 0. But then that implies that ai x to the I is also equal to 0. Ai x to the I to the mi is also equal to 0. Because ai x to the I to the power of mi is just ai to the mi x to the I mi. So in particular, that means that a1x, a2x squared, an x to the n, that all of these are nilpotent elements of R of x. And so what we want to use is an elementary fact, which is that if I have multiple nilpotent elements of a ring and I add them together, that this is still a nilpotent element of the ring. So in particular, this polynomial, which is just f minus its constant term, is nilpotent. But now by assumption, the constant term of f is a unit, and the sum of a nilpotent element and a unit in a ring is a unit. So that implies that f is a unit. Great. So that's the reverse direction. For the forward direction, we want to assume that f is a unit. So we want to assume that there exists another polynomial, which we can call g of x. And I'll write this sum j equals 0 to m, bjx to the j, and such that this multiplied by f is equal to 1. This is what it means for f to be a unit. Okay, so I know that this product is equal to 1. So if I compare coefficients on both sides of this expression, what I can see is that the only constant term on the left-hand side of this expression is a0, b0. And then on this side, I have a 1, and then all of the other coefficients are 0. So in particular, this tells me that a0, b0 is equal to 1, and then that all of the other terms, if I FOIL this out, are equal to 0. So notice that this implies that a0 is a unit, and also that b0 is a unit. And the fact that a0 is a unit is kind of half of what we were trying to prove. So now we want to consider the remaining coefficients. And we can notice that the highest degree term in the product of these two polynomials is x to the n plus m. right? Because this is the highest degree thing that I can get if I multiply something in f times something in g. But now we want to notice that the coefficient here is an times bm. And so this tells me that an times bm is equal to 0. So this isn't obviously useful yet, but now if we consider the next lowest degree term, so this is the x to the n plus m minus 1. So there are two ways that I can multiply coefficients of f and g to produce this term. One way is that I can take an times bm minus 1. And then the other way is I can take an minus 1 times bm. But now what I want to notice is that I can multiply through this expression by an, and I can use this equality. So if I do that, I get that an to the second power bm minus 1, and then plus this term times an is equal to 0. But if I multiply this by an, I just get 0 because of this equality here. So this tells me that an squared bm minus 1 is equal to 0. So I can keep doing this recursively with lower degree terms of the polynomial, with lower degree terms of fg. And what I'll eventually be left with is an to the m plus 1 times b0 is equal to 0. Okay, but now we want to notice that from before, b0 is a unit, and so I can multiply both sides of this expression by b0 inverse. And that just gets me that an to the m plus 1 is equal to 0. Great, so this proves that the highest degree term of f is nilpotent. So now what we can do is we can take f and we can essentially apply the same argument to all of the remaining coefficients of f besides a0. And so the way that we do that is notice that f of x minus an x to the n, that this is still a unit. And again, I'm using the fact that the sum of a nilpotent element in a unit is equal to a unit. And this is a unit by assumption, and then this is nilpotent, which we just showed. Right, so this is a lower degree polynomial that looks like this. But now we can essentially apply the same argument, that because this is a unit, we can multiply this expression by some other polynomial. We'll get that the highest degree coefficient of this polynomial times the highest degree coefficient of the other polynomial is equal to 0. And then we can apply the same recursive argument to get that the leading degree coefficient of this polynomial is also nilpotent. So if we repeat that for all of the coefficients of f, except for a0, we get that all of the other coefficients of f are nilpotent. And that's exactly what we were trying to show. And that's it.